Today on ADG Mod, we're going to be making an entire game using MegaZeux. This is why it took an extra couple weeks to put this video together, as I expected the process to go relatively fast, but then there's an old adage that whatever you think your development time is going to be on a small project, double it. And that's effectively what happened this time around. In fact, as I'm voicing this script, the game still isn't done. I mean, it's close and should be done once I get this video out, but it means in order to get this video out at all, I've had to take a different approach to it than expected. Originally, my thinking was to showcase the process as it happened and demonstrate the different things I was doing, but in the end, I decided what would be more practical would be to show things already working, then go over the mechanics as to why they work the way they do. I'm still going to go over a number of basics, of course, and I'll show some footage from the actual development process, but for the most part, this will be more of an overview than a step-by-step tutorial. However, there are a few stipulations to keep in mind as we go forward here. The first is that I haven't made a game in MegaZeux since like 2001, I think? Yeah, it's been about 2 decades since I actually developed anything with it. Save for one point where I went back to fix a version difference bug with one of my releases. So I was absolutely a bit rusty trying to get started in this again with a blank slate. But it only took a few days before it all came back to me, along with remembering some of the incredibly inane things I used to have to deal with, as MegaZeux does have some shortcomings, at least back here in the old DOS versions. Oh yeah, that's the other thing. Since this is ancient DOS games, not modern Windows games, and because it's been so long since I last used MegaZeux, I decided the best way to ensure that this was working exactly as I remember it working was to stick with the last commercial DOS release of the program, version 2.51. Suffice to say, there's some major restrictions when working with a version this old, given that modern releases of MegaZeux don't have anywhere near the same restrictions and are made to run in Windows. But that also means there might be version inconsistencies trying to run what I've made here in a modern MegaZeux release. So if anyone notices any such issues, please let me know so that I can fix them. Now, let's actually get into this. When you bring up the MegaZeux editor, the first thing you're faced with is a blank world with a single board and all the standard defaults in place. So from here, what do we do? Well, the first thing to do is decide exactly what kind of game to make. And I didn't want to go with anything stock because that wouldn't make for a very enlightening video. But I will say it is very possible to make a game here in MegaZeux with only a minimal amount of code, as there's a ton of built-in objects you can work with, separated into 8 categories: terrain, item, creature, puzzle, transport, element, miscellaneous, and objects, which you access with the F3 through F10 keys. Now, I should also point out that the page up and page down keys cycle the displayed list of shortcuts at the bottom of the screen, but all shortcuts work at all times. So since I didn't want to make a game which felt too stock, I next needed to decide what my main mechanic was going to be. Now, one of the things which bugs me about MegaZeux games in general is that virtually all of the games made in it, with an action focus, rely on the player firing bullets to harm opponents, as shooting bullets is the main method of attack in MegaZeux, just as it was in ZZT. However, because MegaZeux offers so much power with its built-in scripting language, known as robotic, I decided the main way to help make the game stand out would be to change the method of attack. And thus I decided I would base the entire game around player-fired lasers, while at the same time giving the player multiple colors of lasers, which are considerably more effective when used against enemies of the same color. This presents multiple problems right off the bat. Firstly, there's no built-in methodology for having the player fire lasers. The lasers present are generally used to create barriers that you have to time your movements through. They can be fired from robots, with robots being the standard programmable objects in MegaZeux that you'll be working with, but the player themselves is not capable of firing lasers. And secondly, none of the built-in enemies respond to being hit by lasers, meaning every enemy we intend to have in this game will need to be a programmed robot, and that's going to rapidly cut into how much code and robot space we have, as there's a hard limit of 199 robots per board and 61 kilobytes of scripting memory per board. Thirdly, there's only one kind of laser wall in the game, not multiple, so we need some way for the enemies to be able to tell what kind of laser they're being hit by. We can cheat a little with that one. Since the lasers instantly travel from point A to point B, we can just assume whatever laser the player has selected is the kind of laser an enemy is getting hit by, since unless the robot is shot with the laser directly, they will not walk into it on their own accord, as the beam will appear as just a solid object to the robot while it's still in the world. The last limitation we have to keep in mind is that there's a hard limit of 50 active counters, with each counter effectively being a signed integer, where any counter with a value of 0 simply doesn't exist. Now, there's a bunch of built-in counters, some global, some local to the board, and some local to each individual robot, but for the most part, we're pretty limited here. In fact, the only local counter each robot has, which we can manipulate in meaningful ways, is called loop count, which is normally used for handling count-limited loops in the code, but is often the best stand-in for tracking things like hit points. So, because of all of this, one decision I was able to make fairly quickly was that we were going to have a static overlay for every game board. Now, overlays are used to render things over top of the main game world, thus having a static overlay would allow us to show status indicators on the screen and effectively use those status indicators to hide any robots being used to process game mechanics. If we go into the board settings here, we can see that there's 4 overlay settings: none, normal, static, and transparent. The none setting doesn't save any overlay data at all, and you would only use it if you have no intention of having an overlay on the board. The transparent mode does save and allow editing of overlay data, but doesn't render any of it, basically just keeping it ready for when you need it. A normal overlay scrolls with the viewport and is typically used when you want to have elements of a scene rendered over top of other elements. A static overlay is always rendered from its top left corner, and thus is perfect for when you want status bars or other such things which stay stationary while the viewport moves around. Going into the board's size/position settings is what allows us to adjust the size of the board and the viewport. Now we're going to make the viewport fill the entire screen, thus 80 by 25 large, originating from coordinates 0, 0. But in terms of the size of the board, we're a little limited here because in order to make our laser mechanics and enemies work, using as little code as possible, we kind of have to rely on there being a definitive maximum height, which will make more sense why that needs to be the case later on. But I decided every board in the game would be 160 by 50, exactly 4 times the size of the screen space present, which is generally a good size. Obviously, you can set this all differently in your own game on a per board basis, but again, because of how things are going to work in this game, it's really important that we have the exact same height for every board. Now I decided to place the status bar on the bottom of the screen, meaning the last row on every board is going to be where we hide all of our processing robots, as well as copies of the enemies that we want to use. And one of the things which is neat about making MegaZeux mechanics is that it often involves a high degree of parallelism, whereby instead of having one large piece of code which processes everything, you have multiple pieces of code which send data to each other and each processes its own thing. I ultimately ended up with quite a few robots down at the bottom, each of which is important in its own right. The bottom left corner is the laser firing robot itself. Next to that is a bomb throwing robot. The 2 next to that are used for a couple special overlay elements, as we'll go over later. Then those 4 colored exclamation points each handle recharging the 4 individual laser colors that we have. The next one handles selecting different lasers. The next one handles fast charging lasers when the player has ammo. Then the last 4 exclamation marks all handle rendering different elements on the status bar. And then after that is everything to do with enemies, including the enemy robots themselves, as well as a robot which handles spawning waves of enemies, and a robot which handles advancing waves when they're cleared. So yeah, because of the limits on robot counts and memory, it was clear I wasn't going to be able to just populate a board with all the enemies I wanted all at once. So I opted instead to have waves on each board, whereby when you cross a trigger line, the wave spawns in and locks all the entrances and exits to the room. You then have to destroy every enemy robot in the wave in order to clear it and move on. Now, before I start going through the code of how all of this works, let me demonstrate the raw gameplay. So generally speaking, each map has a number of waves to face and sometimes a puzzle of some sort to solve. When a wave is triggered, the enemy robots will only spawn on the colored floors, so you know ahead of time where the spawns will take place. You then need to use your lasers and bombs to defeat them. The game world is intentionally very stingy about handing out explosives, as they're more so meant for utility purposes, and most but not all of the enemies are either resistant or immune to the blasts. Generally speaking, enemies will only take between 1 and 4 hits if you use matching lasers, but will take 4 times as many hits to take out using the wrong laser colors. Well, this is pertinent because early in the game, your lasers don't recharge very fast, so if you run low on power for a particular color, you'll need to switch to a different color in order to keep the damage flowing. Well, this sometimes means burning power on colors which aren't going to be particularly useful for a fight, but every bit of damage helps. When an enemy is destroyed, they have a chance to drop an item, either gems, ammo, or health, depending on the kind of enemy. With gems in particular, they are always magic gems, meaning they always award a single hit point when collected. In fact, let me quickly show you all the adjusted damage tables because that was one thing I very much needed to retool for the sake of this game, given that instead of having 100 health units, the player now starts with only 20, and can ultimately upgrade this to a maximum of 50. Because of this, most built-in objects now only do 1 or 2 points of damage, except for the built-in enemies, which I didn't bother adjusting since none of them are ever used anywhere in this thing, because again, they aren't able to respond to being shot by lasers. So, how does all of this work? Well, first, let me show you the global robot I have in place. The global robot is named Help System, since it's used to show a help screen when the player presses the H key on the keyboard. But when the world is first booted up, the global robot sets all of the default values the game will be tracking. This means setting the actual max health value to 20, setting our own max HP counter to 20, since one of the mechanics needs to know what the current maximum health is, which is not actually possible to do otherwise. Setting HP bar to 9, which is part of the mechanic which allows the HP gauge to work the way it does. Setting the currently selected laser to 0, setting all 4 laser charge levels to 100, and giving each laser a charge rate of 8, which is actually more of a delay value than a rate, but that's just how it ended up being named. The rest of the global robot is raw text used to show an introductory screen when the game first begins, as well as the aforementioned help system. In fact, this text is the main reason why the global robot is a full 5 kilobytes in size, as anytime you need to put a string of text characters enclosed in quotes into your code, you're burning a lot more memory than just raw code, as the code itself is distilled down to single bytes or 2-byte integers of data internally, but rendered out to the screen with words which make sense. This is what's called interpreted code, and it's how a lot of other languages work, including BASIC. Now, the reason some of the text lines start with a square bracket while others start with a percentage symbol is because the ones with the percentage symbol are actively looking for color codes in the text to change the color of the text at certain points. If you try to put color codes into lines rendered with a square bracket character, they'll just be rendered as the raw text itself. This global robot also has a debug menu I can bring up by pressing the U key for when I'm testing specific parts of the boards that I'm building. In the completed game, this debug menu will be zapped out of existence, but you can always edit the game file and re-enable it if you want to cheat. The upper left corner of every single board has a robot blended into the walls, which serves a very special purpose. The instant the board loads, this robot will immediately run this code before anything else can happen, as boards are processed from left to right across each row, starting from the top and going to the bottom. In fact, because of this processing, you generally want to put all of your mechanic handling robots on the topmost row of the board or the bottommost row, depending on how everything's going to work. Now, this special robot designed to reset things first starts by locking the player's ability to attack. Now, this may sound counterintuitive, but there's a reason why we want to do it this way. If we go back into the board settings, you'll see 2 of the options determine if the player is allowed to shoot or drop bombs. Now, if we disable these abilities, then pressing spacebar delete, normally used for shooting or bombing, will generate an on-screen message telling you that you can't do that. So we don't want those messages cluttering the view while we're trying to fire lasers, but if we don't turn these off, then the player would normally be able to fire bullets or generate out of ammo messages. So instead, to ensure none of that happens at all, we just lock the player's attack abilities so we can handle it all manually. This means we also need to manually handle bombs too, but there's a special way I decided to deal with that one. Anyways, the next line in this board resetting bot sets the message row to 0, so that on-screen messages will show up at the top of the screen instead of the bottom. Now, just like with locking the player, this is handled on a per board basis, so for the sake of this game, always needs to be set on every board. The next 5 lines set counters related to handling the enemy waves, as in order to track a wave properly, each robot needs to count up when it's present and count down when defeated. This didn't have to be separated per bot color, but I did it this way on purpose for easier tracking and debugging. and because I knew I wasn't going to be coming too close to the counter limits. And the robot ends with a simple start command to show an on-screen message, in this case, the name of the board that we're on. Now let's get to the more interesting robots. First up is the main mechanic which this entire game is focused around, firing lasers. Now, this robot's pretty sizable because there's a lot of stuff it has to do, but let's walk through it. The first thing it does is set its cycles count to 1. Now, MegaZeux 2.51 defaults all robots to a cycle count of 1, if they don't specify their exact cycle count. But it's just habit for me to have the cycle count defined when a robot does not need to act immediately, given that calling the cycle command itself introduces a delay into the robot's code. Now, cycles are effectively frames of gameplay, so when you tell a robot to have a cycle count of 1, that means you want it to act every cycle. If you give it a cycle count of 2, it would only act once every 2 cycles. Cycle 3 would cause it to act once every 3 cycles, etc. Though these waits between cycles will be interrupted if the robot is sent to different commands or has other label events triggered. We're also having our laser firing robot set its internal loop count value to the currently selected laser. Now this is because we want this robot to change its color when the player changes to a different laser, and we thus need a way to detect this. In fact, you'll see that the start of this robot's handling loop is checking exactly that, to see if its internal loop count no longer matches the laser selection, and in that event, it seeks to the label cell ampersand las underscore cell ampersand. So, one of the fun things MegaZeux is able to do is place the current value of a counter into any string when it's processed. Now, normally you would use this to show different values of a counter on screen, but you can also use this power to inject the values of counters into label jumps, or can even inject counter values when accessing other counters, effectively making for very rudimentary arrays, which is something you're actually going to see in a little bit. Well, the way you do this is to enclose the name of your counter in a pair of ampersands, or if you want to render an ampersand itself, you just put in 2 ampersands with nothing between them. Because the las cell counter only ever ranges between 0 and 3, this means this code will jump to labels of cell 0, cell 1, cell 2, or cell 3 if and when the laser selection is changed. The next section of the code sets loop count back to the current laser selection, assuming it's been updated by this point, then checks to see if the player is holding down the space bar and jumping to an appropriate section of code if they are. If none of this is happening, a wait1 command intentionally pauses the code at this point for the remainder of the cycle, then resumes on the next cycle as there's nothing else for it to check. Next up are all of those cell labels, which simply change the color of the robot to the appropriate laser color. And next are all of the check las labels, which respectively check to see if there's enough power in their respective lasers to allow firing the laser, with 8 points of power being the requirement to fire. If this check succeeds, the power is reduced from the laser, then the code jumps to the fire laser label. Now a check is made to see if any of the directional buttons are also being pressed, jumping to an appropriate label if so, but if no directions are being pressed, a series of no-shot labels returns the decremented laser power and jumps back up to the done label earlier in the code. It may seem weird that if no laser is being fired that I'm effectively decreasing the laser power and then giving it back, but because of the limitations of what I can do with the code, waiting to do the power check and reduction after checking for a direction key would require a lot more code, and code memory is very much at a premium here. So the less you can use and still make things work right, the better. Now, each firing section of the code for each of the 4 cardinal directions has a lot to it, but save for their cardinal directions and coordinates, they're all identical. So we're just going to focus on the north firing one. But first, we manually set the global player face stir counter to 0, 1, 2, or 3, depending on which direction the player is about to fire a laser in, 0 for north. Next, we play a sound effect. Most of the sound effects I'm generating through my robots are built-in sounds, which can be played back more cheaply with the sfx command. But for the sake of the lasers, I decided to create their own unique sound effect using the play command instead. I'm not going to go into how PC speaker effect strings work, as there's a whole section detailing it in the MegaZeux help system, and I'm also not using digitized sound effects or even music for that matter, because that would all just make this game take way longer to put together. The next 2 commands have both been prefaced with a special line which says rel to player. The rel command is considered a prefix command, which means to treat any coordinates or conditional checks in the next command as relative to something else. This isn't compatible with everything, but it is compatible with quite a few things. The first line here would normally check to see if the robot was being blocked to its north, but because we prefaced it with rel player, we're instead checking to see if the player is blocked to the north instead. If so, a special section of code is run, which we'll check out in a moment. The next line would normally duplicate the entire robot presently running all of this code to the board coordinates 0, -1. But again, because it's relative to the player, it's instead placing the duplicate on the same x coordinate as the player and one tile above the player's y coordinate, since this is the north firing section of code. We'll then send that new robot to the north of the player to its laser end label, wait 4 cycles, then return to processing the laser handler as usual. The reason for the longer wait is so that if we fire multiple lasers in the same direction, they don't interfere with each other. Now, if the robot was successfully duplicated, the duplicate robot is sent to this special section of code which fires a laser wall which will only last for 2 cycles, then proceeds to a final section which simply does a little animation by cycling through some different characters, then the robot dies, removing itself from memory since we only needed the duplicate for the sake of producing the actual laser. However, if there wasn't enough room to place the duplicate robot, we instead simply send the laser message to whatever the player is facing. And normally when a robot is shot by a laser, it's sent to the laser label, spelled with a Z as all lasers are in MegaZeux. But there's nothing stopping us from manually sending a robot to this label, thus allowing us to effectively shoot lasers at point blank without generating the actual beam. And yeah, that's the entirety of the laser firing robot code. It's actually not that complicated when it comes down to it, especially given that it has to handle multiple colors. In fact, that's why we have to change the color of the robot itself, because when a robot fires a laser, the color of the laser matches the color of the robot that's firing it. And because we're duplicating the robot, the character we've assigned to the robot by default is the first frame of the animation that it normally plays out. There's a particular reason why we're duplicating the entire robot as well, instead of copying some other smaller robot to save on memory. The thing is, when you duplicate a robot, the duplicate is placed over top of whatever's already on the board without replacing it. This means if you duplicate something over top of a lava tile or some goop, that lava or goop will still be there once the robot moves or dies. If you instead copy a robot from one location to another, you're also copying the floor status of that tile, given that flooring is kinda handled in a weird way in MegaZeux. Now unfortunately, there wasn't really a good way around this for spawning in waves of enemies, so that's why when the enemies spawn in, they leave little gaps in the floor where they spawned, as they're effectively replacing those floor tiles. Now next up is the bomb handler. Since I had to take manual control of the player's bombs, I decided to make them a bit more interesting and useful. The first line of the code in here tells the robot to become a lava walker. By default, robots are unable to walk over lava. If they try, it'll generate a thud message, but will not show that they're being blocked in that direction. Thus, if you're having a robot walk automatically, remember to keep that distinction in mind. Becoming a lava walker is necessary so that our bombs can fly over top of the lava. Next up, however, is a fun little line which is checking the robot's current Y coordinate, and if it's less than 49, it runs a separate section of code based on the direction the player is facing in. This is why the height of the boards for this game all have to be the same, is so that every robot I make down in this low row of the board will either stay idle or handle itself differently unless and until it shows up in the active play area. Now, while the robot is down here, it runs a check to see if the player's pressed the delete key, as that's the normal bomb dropping key. And if the player does, it runs a check on the player's high bombs count, and if there's 0 or fewer, it goes to the empty label above, which plays an appropriate sound effect number and shows a message, waiting 4 cycles before running the check for the delete key again. Now, I could have used low bombs instead of high bombs or differentiated between the two, but I decided to just stick with high bombs for everything in this game. And normally MegaZeux lets players pick up 2 different kinds of bombs with 2 different sizes of explosions when laid. Also, the reason for doing a less than or equal check on this is just for sake of safety. This counter should never drop below 0, but if it miraculously did, we can be sure we're never going to throw negative bombs. The next section of code is similar to the laser firing code from before, except this time, if the player is blocked, it simply skips tossing the bomb at all. Now if the player is not blocked, it duplicates the robot, then proceeds to a special take label, which takes one high bomb from the player, then waits 18 cycles before running the check for the delete key again. This long wait is to ensure that if the player tries to toss multiple bombs in the same direction, that the blast from the first doesn't interfere with the movement of the next. However, notice we didn't send the duplicate to any special section of code. By default, a duplicated robot will start its code execution from the very beginning. Thus, instead of passing the check for the row number it's on, that check will hit, and it will instead go to one of the go labels which have been set up. Now, each one sets the robot to automatically walk in a particular direction, then a slash command tells the robot to follow a basic sequence of movements, in this case moving just one tile. Yes, there is a go command, but for moving just a single tile in a very specific direction, it takes less memory to use the slash command instead of the go command. And we need to do this at all because walking doesn't take effect on the first cycle that it's called. The bomb then plays through an animation sequence as it walks in its designated direction, and ultimately plays an explosion sound effect and explodes with a blast radius of 7. Next up is the code for the laser chargers. And there's 4 of these, one for each laser color, but each functions the same way. They run a loop, checking to see if the amount of charge in their respective lasers is below 100. If so, it runs the charge code, which waits for the number of cycles set by its rate value, then double checks to see if the laser charge has hit 100 during that delay, and if so, returns to its normal loop, but if not, increases the laser charge by 1, then goes back to its normal loop. Now, something that's a bit dangerous here is using a counter with the wait command. Internally, the check MegaZeux runs to determine if a wait is expired or not is an equivalency check, meaning once the exact amount of cycles have passed, the code continues. Thus, if that counter changes to a smaller value while the wait is in progress, it can end up causing the check, which would end the wait, to be skipped, and thus it would have to overflow the byte value it's stored in before the wait would finally conclude, which would take about 256 cycles. That said, there's only one item in the game which adjusts the rate values, and when it does, it intentionally sends the laser charger robots back into their normal loops so that everything I just described doesn't have a chance to happen. The laser selection robot normally just handles the key presses for changing the active laser. Either 1, 2, 3, 4 or ZXCV, either set of keys work, and just set the selection accordingly. Since this robot doesn't have anything else to do though, it also runs the code which writes the current laser rate indicators to the overlay when told to do so, or when the board is initialized. Now in order for this code to make sense, I need to show you the character table I'm working with. Since MegaZeux is effectively running in text mode, it only has 256 character glyphs you can utilize, each made up of 8x14 pixels. But you have full creative reign over what these characters look like. Thus why I even went so far as to alter the font to my own design. However, for the moment, we're primarily interested in characters 237 through 240, which are the upgrade level indicators for the lasers ranging from 1 to 4. Going back to the code which updates the overlays, first we set a temporary counter Z to the rate of the red laser, which will be 8 at upgrade level 1, 6 at level 2, 4 at level 3, and 2 at level 4, thus decreasing by 2 for every 1 increase in level. Next, we divide Z by 2, so we'll now have a value between 4 and 1. Next, we set another temporary counter, ZZ, to 241 and decrease it by Z. This effectively gives us a number between 237 and 240, depending on the upgrade level being 1 through 4, which is what we want. Thus, we finally put a character on the overlay with a light red foreground and dark red background, using the value of the ZZ counter as the character we want to place at coordinates 31, 25. Now, the actual status bar on screen is actually on row 24, but row 25 contains elements which are used for copying from on every cycle. So any change we make there is going to be permanent, whereas anything we put on overlay row 24 will only last until the next cycle because that's how I've coded it in the upcoming robots. The rest of the code here handles the remaining laser colors in much the same way. Now, there's also a special robot down here called Force Recharge. Now, in order to keep the gameplay flowing, I decided to make it possible to collect ammo to rapidly recharge the lasers. Thus, the way this works is it starts its loop by waiting a cycle, then attempts to take one ammo unit from the player. If it fails, it loops back to the top, but if it succeeds, it now runs down the list of all 4 lasers, and for any laser with less than 100 units of charge, it adds 1 point to it. This is why the laser charging code earlier needed to double check after its delay if it still needed to charge or not. Otherwise, we could very much end up with lasers charged to 101%. Next up are several robots which are used to write status indicators to the overlay. The one for gems and bombs are both very simple, but because I wanted them to be right aligned with trailing zeros, I needed to put in some extra code to make those checks and write to the overlay appropriately. The way the write overlay command works is you give it a color, the line of text to show, and the starting coordinate of the text. Actually, you may have noticed coordinates play a huge factor in how things tend to work out in a MegaZeux game, so it's important to become extremely familiar with the debugging window, which shows the current coordinates of your cursor at all times, as well as memory status. Also note that the global robot gets its own separate memory buffer, so try to keep any super large text walls you need in there so that they don't eat into your memory limit, as even scrolls and signposts eat into robot memory. The laser status updating is a little different, but still fairly simple. It begins by copying a small block of the overlay in order to start fresh with all the laser status indicators. It then replaces one of the indicators with a special symbol to indicate which laser is selected. Then it runs the same kind of code as before, right aligning the various laser charge levels each in sequence. And this would probably be a good time to point out that each robot cannot run an indefinite amount of code every cycle. In fact, the limit is quite low, I believe around 40 commands, before it's forced to stop and wait for the next cycle. Thus why it's often a good idea to split complex tasks across multiple robots in sequence. This is also why I end all loops of my code with a wait command, so that I know all of my code is synchronized appropriately, something that's extremely important to do even in modern multi-threaded software development. Next up though, we have the robot which renders the health bar. This robot's a little confusing since I opted to make a health bar able to show up to 2 hit points per one character tile, excepting the ends of the bar, which can only show 1 hit point. This is part of the reason why we needed to track maximum hit points in a separate counter, but also why the HP bar counter was set to 9 instead of 10, as it's measuring the amount of character tiles between the 2 endpoints. Each maximum health upgrade in this game gives +2, which means each time we grab one of those, we simply increase the HP bar counter by 1. However, most of the code here for actually rendering the health gauge to the overlay is just a mass of coordinates and basic math, so I'm not going to explain it in detail. However, I will say that it has a number of special checks in place to help simplify the process and save on memory, as it has 5 different methods in place for rendering the health bar. HP 0 if the player has no hit points or lives left, since this will show up very briefly before the transition to the game over screen. HP 1 if the player only has 1 hit point left, HP max for when the player has full hit points, and then HP odd and HP even, which calculate things slightly differently in order to properly display the HP bar with an even or odd number of hit points remaining. This isn't the most elegant way to do all of this, but it's the most memory efficient I could think of given how MegaZeux works. Now let's talk about how the whole enemy waves system works. Every area of the board which is made to be a fight has a trigger hidden somewhere in it named wave end start, with the n being the wave number between 1 and 7. This robot itself starts off with an idle routine which waits a cycle, then runs several checks. First, it checks if the player is on the correct wave or not. If so, then it checks if the player is aligned with the robot either vertically or horizontally depending on the kind of invisible line we want the player to cross to trigger the wave. If the player is aligned, we then check to make sure the player is below or to the right of the robot, as these wave start robots are only ever hidden in northern and western walls, by seeing if the robot's coordinate relative to the player is greater or equal to 0 or not. Yeah, one of those curious little limitations of the robotic language, at least here in this old version of MegaZeux, is that it's not actually possible to get the player's exact coordinates. You can check to see if the player is at given coordinates, but you don't have access to the coordinates themselves. As such, when you want to do any kind of complex checks against the player's coordinates, you have to get a little creative. Now, each robot has read-only counters called this X and this Y, which store its own coordinates. If you use the rel player prefix, those coordinates are now adjusted to treat the player position as 0, 0. So instead of detecting the player's relative position to the robot, you're now checking the robot's relative position to the player. Yeah, it's a little backwards, but it was the simplest way to make this work. Some of these wave robots also do an additional check to make sure the range to the player is below a certain amount, but if all the checks succeed, that means it's time to lock the player in and start a fight. Now, this always kicks off by changing two very specific kinds of custom floor tiles into very specific kinds of custom block tiles, thus raising the barriers, as it were. And these are color coordinated to the various waves as well, for sake of simplicity. The robot then announces with a message that the wave has begun and sets a number of SP counters, which aren't going to make a lot of sense at the moment, then tells a special wave spawner robot to go. When the wave spawner robot is done, it will tell the appropriate wave start robot to run its next section. And if there is a next section, it will zap one next label, set new SP values, and again tell the wave spawner to go. Zapping a label is interesting, and part of the reason why it's not possible to instance MegaZeux robots, if you're familiar with that term. But if not, don't worry about it. When you tell a robot to zap one of its labels, it scans through its code and invalidates the first instance of that label it finds. That way, the next time the robot is sent to that label, it will instead skip the invalidated label and jump to the next one it finds, which is still valid. Or if it finds none, it simply won't do anything. You can restore zapped labels with the restore command, or you can even pre-zap a label by using the pipe character instead of a colon to define the label. However, when the wave start robot is finished spawning enemies, it sends a different robot called Wave Advance into a loop, then becomes a custom block representing its hidden appearance, thus removing itself from memory since it's no longer needed. Now let's check out that wave spawner and see what it's doing with all of those counters that we're setting. The first thing it does is decrease SP count by 1, as it's going to be using SP count for the sake of a loop, and the way loops work in the robotic language is inclusive of the first run of the loop. So if you tell your code to loop once, you're effectively running the code twice. Since SP count is used for such a loop and is controlling the number of enemies spawned, we want it to loop one less time to get the appropriate number of spawns. However, the next little bit is very clever. SPBot 1 through SPBot 4 are set to the X coordinates of the kinds of enemies we want to spawn from row 49 at the bottom of the board. However, an assumption is being made that these will only be set above 0 when we want to use them. Thus, starting from 4 and going down, we check to see which is the first above 0 and set the maximum number of different kinds of bots to spawn based on that, into a counter called SPBM, which stands for SpawnBot Maximum. The actual spawning process begins by setting an SPB counter to SPBM and starting our loop. Now, because we're using counters for temporary purposes, it's extremely important that this code be synchronized to the cycles. Anytime you want to use a counter for temporary purposes in multiple different robots, you have to consider that these counters are global. Meaning if your robot falls out of sync, it cannot be guaranteed that those temporary counters are still going to be the way the robot left them if some other robot used them for its own purposes. So when you're using temporary counters like I am here, in this case X and Y, it is imperative that whatever you do with them be done within that specific cycle. So what I'm doing in this loop is first waiting one cycle in order to synchronize everything and ensure I have plenty of code time left. Then I set X and Y to random values between the SPX1, SPX2, SPY1, and SPY2 values that I'd set in the wave start robot. Those values were effectively defining a bounding box to place spawned enemies within, and we're now picking random spots inside of that and checking to see if there's a floor tile there of any color. If there is, we jump to the place label. Otherwise, we jump back up to the retry label and again wait a cycle so that we don't run out of commands and fall out of sync. In order to place a robot, we're copying the robot from X coordinate SP_bot ampersand SPB ampersand Y coordinate 49 to the random X and Y values that we chose. And notice what we've done here, in that we're accessing a counter using the values stored inside of the SPB counter. This is what allows up to 4 different kinds of enemies to be defined for each round of spawning, as once we've made the copy, we decrease the SPB value by 1, and so long as it's still greater than 0, we continue and loop back around to the start of the loop for the appropriate count we set. Otherwise, we reset SPB to the SPBM counter before resuming the loop. Once the loop is done, we increase SP count by 1 again, just in case we want to use it again, intentionally zero out the SPBot 2 through 4 counters, but not SP-Bot1, mostly for safety's sake, and then send the appropriate wave start robot to run its next label, which as we saw either starts another round of spawning or tells the wave advance robot to do its thing. The wave advance robot is really simple. When it's told to enter its loop, it begins monitoring the 4 bot counts as well as a boss mode counter used on certain boards. If any of these checks succeed, it means the wave isn't over and thus it continues looping. Once all of the checks fail, it means the wave is cleared. The way it handles this is to first show a message indicating the wave number is cleared, and then tells a special wave over robot to go. And most of the time, this wave over robot doesn't exist, but a handful of waves throughout the game have special considerations when they're cleared, and thus this is to handle those cases. But we have to let the player out of their prison, so we do this by setting a temporary counter Z to the current wave number, multiplying it by 16, and then increasing it by 14. This gives us the color value that we're using for the custom blocks we put in place to lock the player in, which replace with custom floors with the same color index as the current wave number. Again, this was all done intentionally to avoid any ridiculous math and save on memory. We then increase the wave counter by 1, and then everything sits and waits until the next wave begins. And yet that's pretty much it for all of the main mechanics of the game. I know some of this may seem really complicated, but most of this was built and figured out in just a couple of days, which, given how rusty I am at this, kinda goes to show just how simple it really is when it comes down to it. The ultimate trick with MegaZeux is exactly as I said at the start, that it revolves around parallelism. So once you keep in mind just how many things are working in sequence and in tandem with each other, you can get it to do all sorts of pretty powerful stuff with relatively basic chunks of code. So if that was as straightforward as it was, why did it take 4 freaking weeks to make the game? 2 words: level design. I envisioned a sequence of events whereby the player would go through 15 simple levels, getting maximum health and laser upgrades every step of the way, fighting the occasional boss, but failed to recognize just how tricky it can be making interesting handcrafted levels, given that I'm more used to making procedural content. As such, it was taking me about 3 days to make 2 levels. Do the math, and 15 levels was going to take over 3 weeks. Yeah, that wasn't happening on a 2-week schedule. In fact, I got quite a bit creative with these levels. I centered it around a story of a post-robot apocalypse where a guy from one of the remaining human factions has been armed with a quartet of experimental laser weapons to try and see if they'll help make it possible to begin reclaiming the world from the robots. You enter into an old city, find your way into a storage facility to power up, pass through an unusual underground path, end up in a bot factory that you decide to permanently shut down, then use its teleportation system to dive right into the heart of a central command complex, where you take out the main control cortex for the city, thus making it safe for humanity to repopulate it, and thus proving the worth of the lasers towards fighting back against the bots in future encounters. To that end, many of the levels have various puzzles of sorts. For instance, in the second area of the storage facility, you discover a collapsed passage and reason that there may be a useful route to follow if you can find a way through. To achieve this, you find a portable drill after clearing the second last wave of the area. By shooting the drill with a laser, you cycle it from an interactive state to a pushable state so that you can move it into position. In its interactive state, you can either turn it on, or there's an option to pull it away from a wall in case you get it stuck somewhere. There's other puzzles too as you go along, and even some special items to find, one optional, one not, which you can use at the cost of gems to give you special powers. And I suppose I should go over how a typical enemy robot works in here, so let's go with a blue ghost bot. Now every color of bots have 3 matching robots, cubs, ghosts, and bears. Each has an eye bot, but they all behave differently for the different colors. And then the 5th bot is unique for each color. Green being snake bots, blue being tiger bots, yellow being spider bots, and red being dragon bots. The blue ghost bot starts off by setting its internal loop count value to 12. This is effectively its hit points. It then proceeds to wait a cycle and then checks to see if it's still on row 49 or not. If it is, it stays off, but if it's not, it turns on. Upon activating, it increases the blue bot's counter by 1 and now sets its cycle count to 6. The thing is, this is an enemy. If it moved around with a cycles count of 1, it would be super freaking fast and nearly impossible to handle. Giving it a larger cycles count makes it slower so that it will do things more methodically. Now anytime it runs its code, it'll run as much as it can until it hits a wait command, until it moves in a particular direction, not counting automatic walking, or until it hits its command limit, which again I make an effort to stay under so that everything's in sync. The main loop for the blue ghost is to move in a random direction that it's not blocked in by one tile, then move towards the player by one tile, then it sets a temporary counter Z to a random number between 1 and 3, and will loop its movement again if Z is not equal to 1, but if it is equal to 1, it will shoot in the direction of the player before resuming its loop. Basically, after every 2 steps it takes, it has a 1 in 3 chance of shooting, which given a cycle's count of 6 means it takes a shot roughly once every 36 cycles, but it is actually random. If the blue ghost is shot with a laser, it first checks to see what the player's currently selected laser is. Again, we can't differentiate different kinds of lasers, but because they move instantly, we can just assume whatever laser the player has selected is the laser that was fired. If the laser selection is 2, which is the blue laser, it goes to a special crit label, with the laser colors being 0 for red, 1 for green, 2 for blue, and 3 for yellow. If the laser is not the right color, then loop count is only decreased by 1, but if loop count has reached or dropped below 0, we again go to the crit label. While this may seem a little weird, it's done this way intentionally because some of the enemies only have 4 hit points, meaning the crit section of code doesn't actually do a hit point check, and doing a second hit point check in this case isn't going to harm anything. If the ghost still has hit points left, it runs its escape code. This changes its color to indicate that it's been shot, sets its cycle count to 1, and has it run away in terror for 4 tiles, alternating between random movement and moving opposite of the direction the player is in. Note that we cannot just set it to be only opposite of the player, otherwise the robot would always just back up, and thus be very easy to shoot again following. It then sets its color back to what it should be, sets its cycle count back to 6, and resumes its normal loop. If the ghost is crit, either by being shot by a correct laser color or running out of hit points, it now decreases loop count by 4, so yes, using the correct laser is 4 times as effective as the wrong color, and runs its escape routine if it still has hit points left. But if not, it first runs the lock self command before doing anything more. The lock self command locks the robot from receiving any messages from external sources. Not even shooting it with a laser will trigger anything at this point. This way, the robot can properly set its cycles to 1, decrease the blue bot's count, then run an animation sequence of the bot being destroyed, followed by a random number check, which will either generate a drop, or if the drop label doesn't exist, it simply dies and disappears. The ghosts in particular run a random number between 1 to 6, with 1 being a magic gem, 2 and 3 being 5 units of ammo, and 4, 5, and 6 being nothing. The last thing to point out is that the ghosts have a bombed label, so they can be hurt by explosions, losing 1 hit point per explosive tile intersecting with it per cycle. So depending on where the blast radiated from, the explosion will deal between 1 and 3 points of damage. As explosions are technically solid and thus the robot cannot walk into them, thus the blast needs to wrap around the bot to do more than 1 point of damage, and will likely hit 2 sides simultaneously at some point, which would only count as 1 hit. Now, most robots in this game are resistant or immune to blasts, but the cub bots have their bomb label just send them straight to being crit, so a well-placed bomb can take out numerous cub bots all at once. Anyways, I think I've prattled on about this game long enough. Hopefully my coverage here gives you all a taste of how simple even a seemingly complicated MegaZeux game actually is, and why so many people flocked to make games with this thing back in the late 90s and early 2000s, and how even to this day there's still an active MegaZeux community over at Digital MZX, which can be found at www.digitalmzx.com. Which yes, used to be .net, not .com, but the .net domain name still works too, at least for the moment, but it just redirects to the .com site. Now if you'd like to download this game to try it for yourself, or to investigate more of the mechanics on offer, such as how the bosses or some of the puzzles work, there'll be a link for it in the video description to the page on my website where you can find it from, and if you'd like to use it as a base for creating your own MegaZeux game, then feel free. Just remember to properly credit me as having created the original multicolored laser engine that you're using. Anywho, that's all for this exceptionally long episode of ADG Mod. Next up, 2 weeks from now, on Saturday, May 7th, will be a proper review, episode 299. And we're going to be taking a look at a game that's all about inflation. And no, I don't mean in terms of cash, so be sure to stay tuned to see what I actually mean by that. Thanks for watching, everyone, and extra special thanks to those of you supporting me on Patreon. Here's just a small random selection of you all.